So, what we will do is I will before we go into the energy harvesting part, it may be useful for you to look at a few case studies. One particular case study which I tried in my lab, I thought I should share that experience with you. Okay. So, let us see one actually the background is this. We were trying to build an energy meter in my lab. Okay. The name of the energy meter is, you can look up, it is called Joule Jotter. Okay. And in the process of building that Joule Jotter, the power supply section, as we have been discussing on power supply for a while now, is the most interesting part, because I encountered some interesting problems there, and I will show you what exactly happened in terms of an oscilloscope snapshot and how we try to avoid that problem, or how we overcome that, actually we overcame that problem, how we overcame that problem. Okay. So, let me take your attention to one particular problem which I actually documented everything well for you, so that we can directly I can directly show you that. So, that comes from this doc file. I have just put down the block diagram. Okay. What we did was, this is a energy meter which obviously is monitoring power, right. It is monitoring the power quality. It is measuring the VRMS, IRMS, power factor and all that, for which you need several sensors. The potential transformer essentially takes care of measuring all the voltage related parameters. The current transformer will take care of measuring all the current related parameters. I output current, IRMS and all of that will come from the current transformer. So, before we get into running the system itself, in order to measure using these sensors like potential transformers and current transformers, the embedded system has to be powered, right. So, this is the chain of the embedded system. You have an AC input 220 volts 50 hertz, step down transformer gives you AC 650 volts. This transformer is rated for 750 milliamperes. You have a bridge rectifier, then you have obviously a lot of ripple and all of that coming up, and then you will see that I have put a 220 microfarad tantalum capacitor. LDO, which is the specification of the LDO is, I have it here, it is essentially it is a TPS 7A47, it is a LDO which is a TPS 7A47 from TI. I am not specifically fan of any particular company, but we just use this because we found this to be the most suitable one, but there are LDOs from Richtech, there are LDOs from Maxim, there are so many other companies which essentially make LDOs. So, you may have to choose based on whatever you have whatever specification that is closest to your requirement, and then accordingly use it. Anyway, it has an input minimum of 3 volts. I have it here, I will just read out for you. V in minimum is 3 volts, V in maximum is 6 volts, then V out is 1.4 volts minimum and V out maximum is 34 volts. So, the input itself, V in min is 3, V in max is 36 volts, which means this regulator that I show you here essentially is it takes a very large input range and can also give you a large output range depending on what you are looking at. Obviously, this is an LDO, right. The input has to be higher than the output, unlike a boost converter where input can be lower also, right, because when you are doing switching, it does not matter what your input is, you just have to if you are building a boost converter, then you obviously have an input which is lower than the output. So, never mind. It has a quiescent current of 0.58 milliamperes, very important specification, but be careful, be a little more liberal here, right. You are not driving this LDO from an energy harvesting source, you are not driving this LDO from a battery driven source, it is not. So, you do not mind even if this IQ goes up a little higher. Why? Because the AC here is because this LDO is taking power from a 50 volt 220 volt 50 hertz power mains. So, 1 milliampere is also fine, not really going to be an issue for you. So, you can be a little more lax on the fact that its ground current, quiescent current is a little higher. So, it is not really a spec that you should be worried about, that is the point. You should not really worry so much about IQ because it is not being driven, the input to the LDO is not from a battery or from an energy harvesting source, that is the point I am trying to hint at. VLDO is 307 millivolt, that means the drop across the minimum V dropout minimum, I think it is the maximum, it is not clear whether it is the minimum or the maximum. Anyway, the drop depends on the differential, the input to output differential. So, anyway, the drop he has mentioned is 307 millivolt, which is okay. I think this is the maximum drop, it cannot be minimum, it has to be the maximum. Accuracy of this LDO is 2.5%, remember we discussed this as an important parameter. Noise in microvolt RMS is 4, PSRR at 100 kilohertz dB is 60, very good, right, 60, 70 is a very good number. You need that because you need a very stable ripple free DC for all your measurement using these very accurate sensors, you will need them, okay. So, this is a very nice number. Output capacitor is ceramic, he says you can put a ceramic. So, just completing the story here, how did this circuit work, how is it rigged together. So, you get 3.3 volt output here, and as you know the LDO requires an input capacitor and an output capacitor. These two capacitors were chosen with a lot of struggle, and I will show you how finally we were able to overcome that problem. Before we go into that, you have sensor and sensor here. Obviously, this is an energy monitoring chip from Analog Devices, it is called the ADE78 series. So, we use the Analog Devices energy monitoring chip. Microcontroller here is MSP430, there is an SD card for storing parameters and for storing the energy values that have been the monitored sensor values from the energy monitoring chip, and then there is this radio chip called CC3000, which ultimately did not work very well for us. So, we had to replace it with some other Wi-Fi module, but nevertheless this being at least a 4-year-old effort, CC3000 was one of the first Wi-Fi integrated chip for IoT applications, and we were perhaps one of the first few to use this chip and also get into a lot of bugs with this chip, lot of bugs, okay. So, before it actually they improved this chip and then they brought out CC3300 and things like that. So, a lot of things actually happened, we will not go into that detail. But anyway, sensor 1 and sensor 2, obviously sensor 1 is a potential transformer and sensor 2 is a current transformer. Current measurement can be made in different ways. You can use a simple CT, or you can use other types of sensing elements as well, depending on what kind of accuracy you are looking for. You may want to use other kind of current sensing as well. There is something called Rogowski coil, right. You can use a Rogowski coil based current monitoring. Obviously, you will need a little bit of electronic, a small amplifier circuit would be required. So, but anyway, so depending on what, in this case we just use a simple current transformer CT, which I will show you as we go along in our building. Now, the beauty is not there, the beauty is okay, this is all fine, good, nice energy monitor and all that. Radio chip, I put down the specifications, maximum current is 250 milliampere, microcontroller active current is 4.5 close to 5 milliamperes, energy monitoring chip which is ADE7953 is 9 milliamperes, LDO, the SDIO, the SD card for logging all the data requires when you are writing up to close to 50 milliampere, and LDO input was 7 volt DC and LDO output, as I mentioned to you, is 3 volt DC. We overcame, and I gave you those values of 2 tantalum capacitors, and we finally chose those two tantalum capacitors because after a lot of struggle, because of this picture. This is really the problem, this is not really the solution. Look here carefully, there was a dip in the, if you look here, there was a dip in the output voltage. And what was the problem? When was this dip coming? How did I measure that? What is the problem statement? Let me read out the problem statement very carefully for you. A snapshot of the LDO, it says here, confirms this. What does it confirm? The system was working satisfactorily each time data was sensed, processed and written to SD card, no problem. Every time you were sensing, every 20 seconds or so we were sensing the values, we were sensing it and writing it into an SD card, no problem. However, radio communication was unsuccessful. A snapshot of the LDO output is shown in figure 3, confirms this. Explain this result and suggest the simplest solution to this problem. Anyway, the solution is the stability of the LDO, where 220 microfarad tantalum input and 47 microfarad at the output actually solved the problem. And what was that problem? How did you solve it and why and how did it work? Anyway, the solution to the problem is stability of the LDO. It was really out of it was not stable, and those values which I showed you actually brought in the stability. And when you have problems of stability, you will have problems of this nature, where the output voltage actually dipped to 2 volts from 3.3, thereby the radio module was not working. Okay, everything was working fine. When you did a communication, they had a problem because communication requires a slightly higher power. The CC3000 required higher power. So how much was that? I did not mention, yeah, it is 250 milliampere, you can see that. This 250 milliampere current which it required, because this is a Wi-Fi transmission, right, it is a module which has a Wi-Fi chip on board, Wi-Fi technology on board, that required a significant amount of current. This LDO is capable, there is no problem. Only issue was stability was an issue because of the input and output capacitors, and because of that the output was dipping to 2 volts, and I caught this on an oscilloscope exactly at the time when you wanted to communicate at 3.3, this line indeed is the 3.3 volt line. It actually dipped down to 2 volts. You can see that each division here, each large division here is actually 2 volts. I have written it down here, and this is obviously going down to 2 volts. So really we solved this problem by introducing by bringing the LDO back into its stable point. So this is really the whole story with respect to the LDO, and a nice case study which I wanted to share with you, our experience on tuning the LDO for specific for a particular application. So dear friends, this is important. Look at the requirement of your regulator, look at what kind of sensors you are likely to connect, look at parameters from the data sheet. Please importantly do not get into too much of theory. Obviously you should know a lot of theory before you start using these before you put your power management block of a IoT system, but look out for these critical parameters which I mentioned, which I read out to you, like accuracy, noise, PSRR and all that, which we discussed actually, right, and accordingly plan your power supply section of your IoT. I want to explain one more part in this power supply section which you will have to encounter sometime or the other. So let us go back and discuss one more part which is also very important, so which is called also the charge pump, which I thought will be useful before we close and move on to this part, right. So this is what we should be really looking at, how to design our power supply with energy harvesting sources. Before that, let us look at charge pump. Okay, all right. So the point is this, there may be many situations where you will have to sometimes you will have to live with certain voltages which are actually available to you directly as you know, just a minute, let me pull out what I want to say. Yeah, so sometimes, yeah, sometimes you will have to power, let us say flash memories, or you want to flash audio and video codecs, you have to power flash memories. Writing for instance requires higher voltage, right, audio video codecs, okay, or an image sensor for instance requires sometimes higher voltage, right, sometimes even displays, right. They all require slightly higher voltages. This is the requirement for your embedded system. Let us draw it on board. You have the embedded system. Let us say this is your microcontroller, this is your rail voltage, let us say this is 3.3 volts, and there are certain sensors connected to it. If it is an analog sensor, this is an analog sensor, you will obviously connect it to the analog to digital port. If the sensor is digital, you would obviously connect it to the GPIO. This is also another sensor digital, right. Then you have different buses, you have I2C, you have SPI, this is 2 wire and this is 4 wire, and you have, let us say, other peripherals which are connected through this system. It could be even flash memory. Flash can be available over, you will have to connect over an SPI flash or an I2C flash, and sometimes while writing to the memory location you will need higher voltages, higher voltage, right. Or let us say you have an interface, this is an interface which essentially is connecting to the display, and this display requires 5 volts, let us say, example, say, right, I will say 5 volts. How do you generate from this 3.3, how do you generate this 5 volts? Okay. Flash memory, sometimes this may still require a rail of 3.3, which means there is no problem, but when you are writing you will require, let us say you want to write to this location, when you write to that location obviously it needs a higher voltage, right. How does it manage, how does it generate this higher voltage from this 3.3? Well, that is a pretty straightforward trick. I will not go into great detail, but I will show you a very simple circuit. Let us say this is a microcontroller, okay, and this is your rail of 3.3 volts and this is ground. What you can do is take one GPIO pin and construct, sorry, let me write it well, right. Take one GPIO pin, actually what you should do is you should not, yeah, you can, of course, there is no problem, there are two ways of doing it. Anyway, we will take one GPIO here and you generate a simple program to generate a clock. This is GPIO, please note, okay. This is a general purpose input, it is a digital port. So, write a small program to generate a clock, okay, and feed this clock here to this capacitor, okay. This I will ground, not this, okay. And what you will get here is, I will put my usual input and output capacitor, and I will get, I need 5 volts, right, 5 volts, bingo, you actually get 5 volts here. And what is this circuit I built here, this part, what is this? Very simple, right. Go back to your fundamentals and look up, you have actually built a Dixon charge pump, basically Dixon charge and pump, charge and pump is charge pump. So, actually you have built a Dixon charge pump, okay. So, and what did, how did you generate this Dixon charge pump, how did you generate this 5 volts? Well, ideally this 3.3 should have become 6.6, but that is not going to work, that is not going to happen because you have diode drops, and therefore you basically I have not added multiple stages as well, I have just added one stage, and with that I just did one multiplication and I put back the final stage, which is this another diode and this capacitor, and then this is nothing to do with the this capacitor has nothing to do with the charge pump. This what I have circled actually is all that is required to create a charge pump, and therefore V out will be n plus 1 times V in minus Vd, right. This is n plus 1, always it will be n plus 1. This is the stage on which you will store all the energy, and in this case you basically have a single stage here. So you can see that if you substitute n as 1 here, you will actually get this 1 and this 2, the first and second, V in minus this V in, this is actually nothing but V in this, and the diode drops that you see here essentially is the drop that will occur across this stage, and the output should simply be this 2 times V in minus V diode drop, which will give you some voltage higher than 5 volts at the output, which you will take and then apply it through an LDO and generate this 5 volts. That is it. This is the simplest possible charge pump that you can think of. You can go on adding stages here. Essentially here I have applied this clock to this stage here, so let me rub it and apply this clock here. Okay, you apply this clock here, then from here instead of grounding this, you remove the ground from here and add one more stage and add multiple stages here, but obviously you will have to take different clocks, right. It cannot be the same clock. You can apply this clock back at the other third stage, generate one more clock and connect it here, generate another clock and connect it to the third stage, and so on. So you can go on cascading this. I will let you look up Dixon charge pump for you to quickly understand how you can build it, but I gave you a very simple circuit by using your existing embedded system itself, your microcontroller itself with its own rail. You can actually build this and generate a stable 5 volt to connect to these display systems or image sensors or audio video codecs or flash memories and so on. This flash memory also, which is you can buy outside and connect it either through I2C or SPI, internally will be doing this charge pump. It will have a charge pump inside its own chip, because while writing you need higher voltage, right. So in other words, this simple circuit which I have circled here, this simple circuit will actually be implemented in silicon and then implemented inside this flash memory. And how do you do that? How do you implement these diode structures in silicon? Well, you have body connected MOSFETs. You can use MOSFET diodes, right. MOSFET diodes, body connected are very common, body connected. I will not get into details, but just to note that body connected diode structures can be easily built. Structures can be easily be built in silicon, and you can essentially build this Dixon charge pump topology quite well. In fact, there are many types. There are cross coupled systems and so on. We will not get into detail. This in essence means that your power supply section, you can use an LDO under certain conditions, you can use a buck converter under certain conditions, you may require a charge pump under certain conditions, right, depending on how you have to lay out your circuit. And this in overall you can also quickly build. I built this in the lab and I actually tested it before I let you know that this actually works. You can choose components accordingly and build these simple systems to get your embedded system IoT device with different rail voltages requirements very effectively. Okay. So this is the story on these devices. Let us now go back and reconnect to this picture that we mentioned, that this power supply is an intriguing part, and you can build it with battery as an input, you can build it with AC as an input, you can build it also with harvesting sources as the input, where solar, TEG, vibration, flutter, linear motion and so on can be used. Let me now highlight to you some important requirements for power block if harvesting is used. Okay, this is the most important thing. So let us go and focus on this important requirements for the power block if harvesting is used. As you know, a harvester is, what is an energy harvester? What is an energy harvester? It is basically nothing but an electrical power source, right. Ultimately you are interested in electrical power, right. You are not interested, you are more interested in the electricity is essentially the purest form of energy, right. So that is what you are looking at, because most of the electronics, most of the IoT embedded devices that we are looking at actually run from electrical power. So you are looking at energy harvester, which is nothing but an electrical power source. It basically operates by absorbing, some form of absorption is there, absorbing energy somehow, energy in some form, and providing you, absorbs energy and provide energy, right, provide electrical energy. So if you say absorbing energy, in one case it is solar energy absorption, if it is TEG it is in terms of temperature differential, right, in the form of temperature differential, nothing but the thermoelectric effect, nothing but the TEGs are nothing but use the, so in one case it will let us get the physics right. Okay, one is photovoltaic effect, and the other is the thermoelectric effect. This is the physics behind generation of the electrical energy, right. So again I do not want to get into the details of all of them, but what is important is, if you are looking at energy harvesting, the power management, from a power management IC perspective, these are basically some basic requirements. So I will rub this out so that you just note that these are concepts from physics, but very importantly what are these requirements if you are talking of energy harvesting IC which you want to build. You want to use an existing energy harvesting IC which is available out in the market. You want to use a solar panel, you want to use a thermoelectric generator, you want to use wind energy, micro wind energy, you want to use linear motion, all these systems are there already out there. Okay. How do you interface those energy harvesting sources to your embedded system such that you will have a perennial working of the complete system, that is the goal, right. You do not want to keep going and replacing batteries, or you may also want to do that I will do all the harvesting for charging a rechargeable battery, that is also another paradigm. Okay. For example, if you are talking of, let us say, a very critical operation, like for instance you are interested in a wearable and a healthcare parameter has to be monitored. If you say that I use a solar energy harvesting, means that only this wearable should be worn during the time, during the day, you should have sufficient sunlight, and only under that condition the wearable actually is able to work, because that is the time when the energy is available. You obviously do not want such designs. It should be seamless, it should work 24/7, it should be able to do the monitoring for you and all that, which means you have to put a battery. Battery is fine, but you do not want to replace the battery for a long duration, which means you may want to keep charging the battery. You do not want to find a charging point where you have to go and consciously go and remove your wearable and then actually connect it, and then actually you want to charge it. That is also not something which is very practical. So you must be able to wear it, and opportunistically to harvest energy and then basically charge the battery, which is in turn used for driving the load. So, energy harvesting can be applied in many scenarios. Directly by harvesting energy you drive the electronic, or harvest store the energy by storing the energy means charging the capacitor or charging a super capacitor, or putting that energy into a rechargeable battery so that the battery keeps charging all the time. So, that is, these are the two basic things. Anyway, essentially if you talk about energy harvesting IC, it should provide the necessary electrical interface to the harvester to ensure one important parameter is the maximum, please complete it if you already know, power transfer, okay, under the ambient conditions. See, slowly from LDO to buck converter to charge pump, we all mentioned many of these systems. All of them made an assumption that there is an input voltage available, input which is a V in is available so that you get V out. But now you are changing your hat, you are saying I do not know when V in will come and I have to do a few things in order to make it work. So, one thing is you do not know when V in is coming. The second thing you want to do is if V in comes, how to extract maximum from that V in, how to get maximum power from whatever energy is available, how do you extract it maximum. So, energy harvesting means maximum power point, maximum power transfer, which means maximum power point tracking becomes an important requirement for energy harvesting power management systems. So, this is number 1, very prime to energy harvesting circuits. And second thing is receive the energy output when conditions are good, receive RECEIV, right, receive energy, receive the energy when conditions are good, okay, and store this, store, very important, store this energy. Where do you want to store this energy? Charge a battery, charge a battery, charge a super capacitor. Both of them will allow you to charge the energy, charge whenever it is available. Then third thing which is a requirement would be to manage the power transfer. You have to ensure that there is isolation. Basically you have to look at isolation. What do you mean by isolation? This is not really either galvanic isolation or any of the electrical isolation. The isolation transformer for instance does a isolation between the input to the output, so that you essentially when you are operating at lower voltages from higher voltages, this isolation allows you to create your own ground for instance and work in the lower voltage domains. It is not that isolation. When you talk about power point, when you talk about energy harvesting, isolation means here in the context of load, load may require let us say 100 milliamperes suddenly, okay, and what you have is a small harvester. You have a small harvester which gives maybe let us say anywhere from 2 to 20 milliamperes based on the conditions which prevail at the by the harvesting sources. Like if there is a lot of sunlight, you may get more than 1,50,000 lux or even 2 lakh lux on bright sunlight, or you may end up with 200 lux, 100 lux if it is inside indoors, right. 100 lux, 200 lux is indoor solar panel, 100 lux, 200 lux indoor, 2 lakh lux bright sunlight, okay, and if there is a cloud it is down to 50,000 lux outdoor, it is down to 25,000 lux outdoor. Cloud passing by 2 lakh goes down to 50,000, may even go down to as low as 25,000, as low as even 10,000 lux, 5,000 lux, and then again go back and pick it back to 2 lakh lux. Sometimes when there is a lot of cloud, when there is a monsoon season, the sun is not out, you can even have 10,000 lux over an extended period during the day, which is very low. The same panel which saw 2 lakh lux, 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 right, LUX, essentially is seeing a very small lux value. So the energy is fluctuating, input energy in the form of sunlight, photovoltaic, the sun energy call it, or the light energy call it, that is fluctuating, and therefore whatever is the input you should be able to extract maximum at the output. That is why you need this MPPT. And load let us say requires 100 milliampere, I gave an example, but the input currents are fluctuating between 2 milliamperes and 20 milliamperes. You must be able to essentially isolate the electrical load on the downstream. Basically I mean isolation downstream electronics. Okay, downstream electronics has to be isolated in a manner that the energy demands of the load, right, of the load, energy demands of the load does not get exposed. That is what we mean by isolation in this context, does not get exposed to the input system, input harvesting system. You cannot say input system anymore, energy harvesting system, because if the load gets connected directly to the harvesting system, there is no way by which the load is going to get that power, right. You have to do that isolation, okay, that is a very important thing. Another important thing, I tell you, this is something that in the last many years researchers have spent enormous time and energy trying to understand what is a clever circuit in energy harvesting, what is that magic mantra, how do you ensure that energy harvesting circuits become very novel, reliable, and all kind of let us say the hype, the wow factor of an energy harvesting circuit really comes from one important parameter, and that indeed is self starting. So many papers you will see in literature which says we will be able to do self starting. See, what does it mean? It simply means if you do not have a battery based system, the whole electronics is going to work with just by harvesting electronics. Let us say essentially means this is an application which is, let us say, doing ambient energy monitoring, where you are not really worried about the ones that I mentioned to you about a wearable electronic. This obviously you have to put a battery and use a harvesting for charging the battery. It is not that example. The other example where you are essentially looking at ambient monitoring, you want a sample, let us say every 5 minutes or 10 minutes or every hour. That electronic is completely energy harvesting based, and that electronic you want to self start, because you are starting with 0 energy to begin with. Somehow you will need to kick start the whole electronics, and kick starting the electronics to start working itself means that self starting is a very important thing, and all the smart electronics, all the wow factor for energy harvesting essentially hinges around this one important parameter, which is indeed the its ability to do self starting. Why is this important? Because harvesting sources, I do not have to say this, but I just want to drive home that you do not forget this important point. Harvesting sources are weak. energy sources, low grade, right, weak energy harvesting sources. Okay. So, you can be asking, I have an energy so at the end you can say I am building this energy harvesting circuit, and the other person can say, is it self starting? Have you solved the problem of self starting? Have you have you solved the problem of isolation of electrical loads which require higher energy? Have you done that isolation effectively? Does your circuit take care of that isolation very well? What is your input energy? What is your source, for instance? When you say weak energy, are you trying to look at energy which is for coming from indoor, or is it outdoor, and so on and so forth. Finally, this is a dream which we have discussed even in the other world. I just want to put back the same dream and the same story all over. It itself should be least energy consuming, right. It is not a big deal, but this is a very important point. So, it should not be a power guzzler itself, least energy consuming, which means you have to worry about the quiescent currents, you have to worry. It can't be like the other examples where you can have 0.58 milliamperes because you are drawing input power from let us say from the grid mains, and you can afford to LDO, for instance, that LDO example which I mentioned to you in the last classes was actually taking 0.58 milliamperes. You can't afford that kind of currents because this is actually a harvesting and precious harvesting energy is being used. So, the electronic itself should be least energy consuming. So, what are these big problems, what are these big bullets when you talk about energy harvesting before we go into circuits, before we go into simulations, is that it should do MPPT, number one requirement. It should be able to receive energy when conditions are good and store this energy, two possibilities of storing energy. It should do isolation of a different type, essentially downstream electronics where the emergent demands of the load does not get exposed to the input energy. Energy harvesting system should be avoided. You should do that isolation. It should do self starting, and it should be least energy consuming itself. Now we will launch ourselves into different energy harvesting ICs. We will look at those simulation circuits, and we will look at building those circuits, and I will also show you practical examples as much as possible for you to say how can I build this power block of my IoT system such that it can have an energy harvesting at its input, energy harvesting source as its input.